Okay, so welcome everybody. My name's Mike Zephyr. I'm an associate professor with the University of Melbourne in the Faculty of Business and Economics. And this is the first Quantitative Methods Network, or QMNET, talk for 2021. And today we're excited to have members of the Mplus team with us today. We have Bengt Muten and Tihomir Asparouhov. And Tihomir today is going to be talking to us about advances in latent variable modeling with Bayesian estimation. And this is going to be a two-talk series. So tomorrow we'll hear from Bengt. And so just a little bit about Tihomir and that. Oh, hold on, sorry. Tihomir has a PhD in mathematics from Caltech, or the California Institute of Technology, which is what Caltech is. And he's been a part of the Mplus team for the last 20 years and has written on finite mixture modeling, complex survey analysis, multi-level modeling, survival analysis, structural equation modeling, and Bayesian analysis, as well as multi-level time series analysis. And Tihomir, if you want to get started here, I'll let you take it away.
Thank you again for inviting me to speak to you guys about what we're doing at Mplus. So I, again, will be speaking about advances that we can do with Bayesian estimation in latent variable modeling. Just a quick chronological overview of the Bayesian estimation for SAM. It's very incomplete and impartial overview here, but the Bayesian estimation for SAM actually, the first steps were done between 1990 and 2010. There was some early work by S.Y. Lee, Armigan, and Muten, and others. And it was mostly focused on this, the basic SAM model with continuous and categorical variables. And it turns out that the estimation is pretty straightforward for these SAM models, but with the exception of two main obstacles that exist there. And the two obstacles are the estimation of the correlation matrices and the estimation of the thresholds in ordered probit regression with more than two categories. And I've listed the three most important works on those, both of these obstacle problems. And, we have enough tools now to deal with these. The Mplus work started in 2000 and until 2010, we basically implemented all this stuff, including all of these methods for the correlation matrices and the thresholds. In 2010, we released Mplus version 6, which included the Bayesian estimation for SAM, multi-level SAM, 2 and 3 level, and cross-classified SAM for continuous and categorical variables. And that also included new modeling such as random slopes and random loadings. And the three main probably features and advantages that that framework gave us was that we can handle an unlimited number of random effects in the modeling framework. We can also handle missing at random with missing data for categorical variables. And I had to insert here a little bit more because in maximum likelihood you also obtain missing at random for categorical variables, but it's not the same thing. So what I'm referring here to is the categorical data version of the EM algorithm for continuous variables. So with the EM algorithm for continuous variables, you can estimate the unrestricted multivariate model in the presence of missing data, but that wasn't possible until the Bayesian estimation was utilized. So the Bayesian estimation provides a multivariate probit model, unrestricted multivariate probit model for the missing at random for categorical data. And then the third probably sort of breakthrough that came about with this implementation was that we can now impute missing data from a variety of models, multi-level, multivariate, multiple group, and actually impute data from any estimated model and mixture of categorical and continuous variables. Next step in the Bayesian advantages for SAM was this basically article published in Psychological Methods that started these models that are called the Bayesian structure equation models. They're kind of special models. They're not. They're in this article actually this methodological framework actually provides. It's quite unique in the sense that we are not using the Bayesian estimator just as a computational tool. Virtually in everything else I'll say today, the Bayesian estimator is used as a computational tool, but not for this model that we introduced in 2012. And the BSEM models, they cannot be estimated with other estimators because they're not identified. And they basically, that framework is designed to discover the structural models. And we use basically tiny priors as a replacement of the concept of a parameter being fixed to zero. So when a parameter is fixed to zero, it's essentially not a part of the model. But we can replace that concept of parameter fixed to zero with a concept that says that the parameter is maybe zero and we're not sure, but we think it's zero. And so basically we provide a very sharp prior with very small variance centered at zero. And basically we allow the data to overwrite that prior and let the parameter escape if it's needed. And so and so it's kind of unique in that respect. Then another important concept is we replace the concept of equal parameters with the concept of parameters are possibly equal, and that's quite important is in multiple group measurement in various studies where in the measurement model for latent factors you generally want to have the measurement invariance. So you can study the differences between the groups for the difference across groups, the differences in the factors across groups. But we can now replace with this framework, we can replace the equality parameters that require strict measurement invariance with the concept of parameters that are possibly equal or approximately equal, or that we are going to let the data decide if they're equal. With this framework, we can also estimate basically these three models that I thought were the most important applications. We can discover cross-loadings in confirmatory factor analysis. And we basically, what with the BSEM model does, it basically adds all the cross-loadings. And of course, that's a non-identified model, but we let the data actually discover the cross-loadings that are necessary. Same thing with residual correlations. For CFA, we add all the residual correlations, and of course, that's another non-identified model, but we let the data decide which correlations need to be added. And then the last application is when we can estimate group-specific factor means and variances without assuming measurement invariance. Again, that's another non-identified model in the maximum likelihood framework. But with this, the BSEM framework, actually, you can do it as well. Today, I'm going to actually be talking about the more recent developments, and the talk basically goes over 4 different articles that we published in the last 3 years. So the first article is the dynamic structure equation models, and that modeling framework basically combines multi-level SEM and time series models. And you basically construct individually specific time series and common filter models that can be used in psychology, for example. And this modeling framework can separate correlations in the data that are due to observations nested within subject versus correlations that are due to observations taken in proximity of time. We also introduced in that paper time series for categorical data through tetrachloric and polychloric correlations or correlations, and that is a very useful model and an alternative to the hidden Markov model. To the hidden Markov model. So, and the second paper is the latent variable centering paper, and we basically going to with latent variable centering, we resolved well-known biases such as Nickel's bias and Lütke's bias, and that paper, we think we basically can improve on the most basic hierarchical linear model. So in a way, this kind of is the very first building block here that we can improve on a very basic model. So the one contribution that actually happens with the Bayesian approach is that latent variable centering can also be done for covariates that have random slopes, and that particular feature is not available with the ML framework. And then the third paper is the interactions paper. We can with the Bayesian methods, we can estimate an unlimited number of interactions, and that also this interactions framework, interactions between latent variables. And that framework also provides one of the most important applications of that is that we provide an efficient estimation for multi-level moderation and mediation models. And those models were proposed almost 10 years earlier, and they've been in circulation, but most of the attempts to estimate were through the maximum likelihood estimation, and that was not particularly, they were very difficult to estimate. But with this latent variable interaction framework, we can now utilize the very efficient Bayesian estimation. And then the last paper that we just published recently, and it's also basically what the Mplus version 8.5 was, is basically we expanded the Bayesian estimation to structural multi-level and mixture models for logit, negative binomial, and nominal variables. And I'm going to show you later on, I'm going to discuss a time series model panel time for panel data that is count outcomes. So through so basically that would be dynamic structural models for Poisson and negative binomial outcomes. And I'm also going to describe a multi-level modeling for nominal outcomes, which is another a little breakthrough that this brings about, and we can now estimate in multi-level models nominal outcomes quite efficiently. And that breakthrough also comes via this polygon distribution, which I'm going to talk about later. So I'm going to start first with latent centering, then we'll talk about DSEM, and then interactions and moderation, and then we'll finish with the counts, nominal, and logic. And so this is the first part, latent variable centering. I'll first quickly go over why, what is observed centering and latent centering, and then we'll talk about Lütke's bias and how we do latent centering with random slopes, and then we'll talk about latent centering for categorical variables, and those can be for categorical dependent variable or for categorical predictor. And so we start here with this most basic model. This is the standard two-level model, and it's described in Raudenbusch and Brick's book on multi-level modeling. And it's basically what we call the observed centering. So you have a dependent variable y for an individual I in cluster J. And here, this is the dependent variable is predicted by the covariate, but the covariate is centered. This is what we call it, is centered. We basically subtract, we compute the clusters, the mean of the covariate in each cluster, and then we subtract that from the actual observation. So that's basically the deviation on the routine level. And we use that as a predictor, and then the actual cluster mean is also another predictor. So we take one predictor and we make two predictors out of them, and they have separate coefficients. And in fact, the difference between these coefficients is generally referred to as the contextual effect, and it's basically the group level effect of the covariate. So the effect of the covariate beyond the individual level effect. And the two important questions here is, why do we actually have to do this separation of the covariate? Why do we create two separate predictors from one predictor? And then the second question is, why do we treat X and Y differently in this model? So for Y, we use a random intercept, which is a latent variable. So we don't actually use the sample mean here for Y, right? We could have used the sample mean, but we didn't. So in the multi-level model, we don't use the sample mean for the Y. So why do we do it for the X variable? So these are the two questions that I'm going to address first. And again, using what we call observed centering, is this centering of the predictor here on the within level with the sample mean. So first, why do we have to do the two predictors? So if you don't center the predictors, then the model would look like that. So you basically just have the covariate here. The first thing is that you don't get two separate coefficients, beta 1 and beta 2. And in fact, if you actually have the two coefficients and you estimate the one coefficient beta 0, the mean of this random slope, then beta 0 is essentially is called an interpretable blend of the two coefficients, beta 1 and beta 2. And it's basically is this weighted mean of the two coefficients, and the weights are inversely proportional to the precision of the estimates. The issue is here that many multi-level studies actually focus exactly on that difference between beta 1 and beta 2, the contextual effects, and it's sometimes referred to as the big fish small pond effect, and it's quite popular in educational studies, and it's pioneered by Herbert Marsh work, this studying the big fish small pond effect. And here's a little diagram from the Random-Distribution-Briggs book, which kind of explains what an interpretable blend is and what happens if you don't split the covariate into two separate parts. So basically, you can see these ellipses are basically the clusters. Now, if you estimate the model with two separate coefficients, you basically, within each cluster, you feed the line, the best fitting line, which is this one in this cluster. And here is this line, and so on. So you get one particular slope for the within level, within cluster, what the relationship between x and y is within cluster. And then if you actually look on what happens in the between level, you basically average the y's and the x's for each cluster, and then you get 3 points, which are basically these black dots here. And if you try to fit those, you get a separate slope, which is beta b here. And then, or if you actually try to fit, ignore the clustering and just try to fit all the data all together, then you're going to get this beta t, which will be basically the dashed line over here, and you get some kind of other slope. And so that will be an interpretable blend of the two slopes that we really want. Next, I will try to address the second question, is why do we actually treat the x and the y's differently? And here's a model that was used by Lütke, and it's called the Latent Covariate model. And here we're describing this without a random slope for the covariate. So both slopes here are the same. But basically what this does is, instead of using the sample mean for x, it says that we're going to deal with this as its own hierarchical model, where this will be a random intercept instead of actually using the sample mean. And that will be a latent variable. So this that will be a latent variable that will represent the mean of this covariate in cluster J, the true mean. And then we can center with that true mean instead of the sample mean. We can center the covariate and use that here in the predictor. So and then use again that true mean to predict the random intercept. And basically, the difference between the observed centering model of Random-Distribution-Briggs and this model, Lütke's latent covariate model, is that we replace the sample mean with the true mean of the covariate. In multi-level SEM context, this actually is written it has a kind of a nice write-up. So we don't just split the covariate, but we also split the dependent variable as a within portion and a between portion. And then the beta 1 coefficient is just a simple regression between the two within level portions. And the second coefficient, beta 2, is just the regression coefficient of the between level components. But both of these are latent variables. And it was shown in Lütke's article that the observed centering does not estimate the contextual effect correctly. Essentially, there's a bias in the beta 2 coefficient, and that Bias is actually given by this formula. So it's basically the difference between the two coefficients, and it's multiplied by this quantity where ICC is the interclass correlation for X, and N is the sample size of the cluster size, basically. And this Lütke's bias, actually, some things to know about the Lütke's bias is that the bias will disappear when there's no contextual effect, and there's no contextual effect when you have beta 1 and beta 2 at the same coefficient. And it will also disappear when the size of the cluster actually goes to infinity. However, it will increase if the interclass correlation goes to 0. And this bias occurs actually because the sample mean has a measurement error, and it's not just the fact that it's not exactly the same as the true mean, and but what it is that you have an uncertainty in the predictor, and that uncertainty has to be accounted for. If there's a measurement error in the predictor and it's not accounted for, it's well known that this produces bias. So there's actually some simulations where people actually would use the exact mean from, and they still get the bias, because it's not enough to actually get a perfect sample mean estimate. You really have to actually have the measurement uncertainty into the model. And Lütke in that article shows that latent centering, the latent covariate approach based on multi-level SAM methodology, eliminates that bias in the contextual effect. And you can, when you don't have random slopes, you can actually do that with ML or with Bayes. When you have, however, random slopes on the within level, so this is basically the same model as the one before, we just replaced now the coefficient on the within level is now a cluster-specific random effect. And in that case, you can no longer estimate that with maximum likelihood efficiently, because you have a product of two latent variables, and there's no, closed form expression for the likelihood. If the coefficient is not random effect, and it's just one parameter that's invariant across all the clusters, then you can estimate that with with maximum likelihood with the closed form expression, or you can use an EM algorithm for the latent variables here. But when you have the product of two latent variables, then that falls apart. Anyway, this model can very easily be estimated with the Bayesian estimation, and actually we've liked it so much that it's now the default in Mplus. And if you actually just write a multi-level regression with the Bayesian estimation, and you have you include the contextual effect like this, then it's going to estimate exactly this model. You don't have to specify anything in particular. Here I'm going to show you a little simulation, and that's basically the same model as the one on the previous page. I just added this equation 5, where the between part of the covariate not only predicts the intercept, but also predicts the slope. And just a little simulation, and the results are right here. And you can see the latent centering. These are basically the bias of the estimates, and then the coverage of the confidence intervals. And this compares the latent centering method with the observed centering method. And you can see that the latent centering method works quite well, where the observed centering has biases pretty much in all the parameters. And that's kind of the point that I'm making here, is that in general, Lütke's bias was defined as something that is specific to the contextual effect, just to the parameter beta 2. That's where when you have non-random slopes, then just parameter beta 2 is misestimated. But when the model becomes somewhat more complicated, and you have the random slopes, then that bias actually spreads all over the place, and it affects all the parameters, as you can see here, and including the coverage of the estimates, the coverage for the confidence intervals. So next, I'm going to describe how we do latent centering for categorical outcomes. And there's, again, two cases. We have the categorical being the dependent variable, and then you have the categorical variable being the predictor. And all the examples I'm going to describe today, they're the most basic examples. They only will have two variables, and just describes the relationships in these structures. Anyway, so here we have a categorical variable y and a continuous predictor x, and we're going to here's the multi-level probit model where we have a random intercept and a random slope. And the first step is, again, we split the covariate as a within and between, and the probit model uses the within portion of the covariate as the predictor, and we'll have this random slope, and then the between part of the predictor is going to have a separate slope. So again, we have contextual effect, and it's going to predict the random intercept. And this model, by the way, features something sort of a novel concept, which would be that we have in this model, we have cluster-specific polyserial correlation, which comes about from the fact that the beta-1 coefficient is actually cluster-specific, and that actually is the way to compute the polyserial correlation between y and x. Without the random slope, if you don't have a random slope here, the model can actually be estimated with the WSMV estimator. It can also be estimated with maximum likelihood, but once you actually get into this latent centering, you're kind of starting to get lost with maximum likelihood. You can estimate it, but so with maximum likelihood, you would have 3 dimensions of numerical integration with this model, this, and that, and it's just less efficient and not as good. But WSMV here would be able to estimate this quite efficiently as long as the slope was not random. But with random slope, we basically would just recommend using Bayes again. And here's some real simulation that shows again that the latent centering works quite well, and the observed centering does not work well. And it again, just as in the previous case with all continuous variables, we see that the presence of contextual effect is what actually leads to biases. And also this Lütke's bias exists even without the random slope, so it's not necessary to actually have beta-1 be random effect here. With non-random effect, you get the same biases as well. The next situation that I'm going to describe is how we deal with latent centering when you have a categorical predictor. So that's slightly more complicated, but it's pretty much the same logic. So first, we would actually take the deal with the covariate, and with the covariate, you basically would essentially estimate for the covariate just a probit model, a multi-level probit model with a random intercept. And so this is basically that equation right here. And if you want to think of this as the underlying variable behind the binary variable here that I'll use, is that the underlying variable x star is basically again separated into a within portion and a between portion. But again, this part over here is nothing more than the random intercept in a multi-level probit regression. And the within portion here, for identification purposes, the variance of that within portion is fixed to 1. And once you actually have this decomposition of the covariate, you can use then the within portion again to be the predictor for y with the random slope, and then the between portion will basically predict the random intercept. And here, basically, the results of this simulation study. Again, latent centering works quite well. The observed centering shows some biases again. And what's important to note here is that, again, when you have contextual effect, the biases are bigger, but the contextual effect, the biases do not disappear when the contextual effect is not in the data. And so there's still some bias here. And that is basically comes about from the fact that when you do observe centering, you're essentially treating the binary predictor as a continuous variable. And it is a fairly well understood concept that there is when you do this model, use that kind of a violation where you treat the categorical variables continuous for the purpose of obtaining the observed centering, you attenuate the correlations. And so the important thing here is again this how I'm judging the quality of the estimation is through the correlation R, which is basically the correlation between the between portion of the two variables. So R is the correlation. So it's kind of scale independent way to measure the biases. And as you can see, there's additional bias that occurs in that situation also when you don't have contextual effect. And also, like in the continuous case, you can see that as the sample size, the cluster size is increased, the bias decreases. So it behaves just like Lütke's bias. And with that, we'll move to the second portion of the talk. We'll talk about dynamical structure equation models. I'll first describe the general model, and then again, I'll go to the most basic model, which is the vector autoregressive model, and with two variables. And then we'll talk about Nikiel's bias, and I will move on to the residual dynamic structural equation models, the RDSEM models, and we'll compare then RDSEM and DSEM, some comparison, and then we'll also compare RDSEM with a restricted maximum likelihood estimation, which is also often used to model panel time series data. So first we start with the DSEM model. The idea behind the model is that we're going to merge time series, structure equation, multi-level, and time varying effect modeling, this concept into one generalized modeling framework in Mplus. And the variables are, you have a time series panel data, Y is the observed data, eta is the factors, X are the predictors, and I and T here stand for YIT is basically the observation for individual I at time T. And there are four distinct sources of correlation in such data. One source is that observations are nested within individuals, and that's basically the multi-level aspect of the model. Another source of correlation is that observations are correlated due to proximity of observation, and that's the time series aspect of the model. And then we have correlations between different variables in the model, and that will be dealt with the structure equation part of the model. And we have also correlation due to the same stage of evolution, which will be the trend part of the model. And basically, this modeling framework is able to estimate all these correlations and attribute properly to the correct source. And the model goes as follows. We basically look for another decomposition of the variables, and here we're going to be decomposing the variables into three separate components. So this is the time invariant contribution that is individually specific. This will be the component that is individually invariant, but time-specific component. So these are both random effects, And then the third component here is basically the residual. So that's deviation from the sum of these two components. And once we have this separation, we can model those three components separately via structural equation models. But to point out that this DSEM model actually has three separate distinct models in it. So if you remove both of these components, then we call this the single level DSEM model. So then you just have that's basically, you have one individual that you're modeling a single time series model. And then if you remove the time specific component, then you get the two level DSEM model. So there's no evolution across time. And then the cross-classified DSEM model, which has these, two separate sources of nesting of the data, then that's basically the full version. And again, each of the three components will have its own structural models, and I'll just go and show you the structural models, but I'm going to start with the Y2 and Y3, and then I'll go back to Y1. So Y2 and Y3 basically is just the standard Lizero model where we correlate, we model the covariance of the components of the vector Y2 through latent factors on that level. And then the latent factors themselves are regressed among each other and on other predictors. And the same happens for the time-specific random effects on the third level. And those equations can include not just the parts of the dependent variable, they can include observed variables that are specific to those levels. And then we're going to move back to the structure equation model on the first level for Y1IT, that residual here. And so this is actually modeled in a little bit more complex way. And now you can, in the predictors here, you can use not just the contemporaneous other variables in the model, but you can actually use any of these variables from the prior L periods, where L is the lag of the model. So you can use Y from the previous period to predict the Y now, and this basically gives you the time series structure of the model. And one thing important thing to note here is that these predictors are the Y1 component, so that's not the original variable, but that is very important that we actually use the Y1 component only. So the between levels are the levels are basically independent of each other. And here, this is the most basic model, which is called the vector autoregressive 1 model. So, and the diagram here is from a paper by Hamaker and others, and it has 2 variables. And as we talked about, you decompose this as the time invariant component of that variable, and then the time varying component. And so this is the within level components and the between level components. And the within level components have a very simple autoregressive structure. Here the variables are time t, and those are predicted by the same variables of the previous time from the previous time period. And what we the fact that there's a black dot over here means also that those regression paths are actually specific to each individual, so they're random effects. And so you get 4 random effects over here from the autoregressive relation, and you also get the 2 random intercepts, and you get a total of 6 random effects in this model. And this is sort of the most comprehensive bivariate model for time series panel data. It also appears to be the most commonly used model from what we have seen so far. And I'm going to, here's a kind of a way of describing the same model with formulas. Again, you have 2 variables, Y and Z. You basically split the 2 variables in within portion and between portion. And these are the autoregressive relations on the within level, where you predict Y and Z at the current time from Y and Z from the previous period. And this model can also be estimated not just with observed variables here. You can actually have those be latent variables that are measured by their own structural measurement models. So just a factor analysis model can be used with some observed variables here that measure a latent Y, and same, and also for Z, and then Y and Z can actually be latent variables. And I just wanted to go through some of these few basic facts about the bivariate VAR model. So the way it was portrayed here, it has just 6 random effects, but actually most often it appears to be that they actually are 9 random effects, because the model can also include subject-specific residual variances here and subject-specific subject-specific correlation. And it turns out that these are fairly important, and they are being included fairly frequently in VAR model estimation. And again, without the within decomposition that we do, without this decomposition, then you won't be able to distinguish between the time varying dynamic and the time invariant dynamic between the variables. And as in typical multi-level models, we borrow information from the entire population to make a very strong model for one individual. How much data do we usually need for estimating a bivariate VAR model like that? We would like to have at least 100 individuals, and the length of the time series ideally would be 30 or more. But often, people try to estimate the model with much fewer data points with that. But this is kind of the baseline that I think we want. In terms of sampling designs, daily diary is the best in my point of view. What happens is that people actually often use multiple times of observations within a day, and also they use random times of observation within a day, and that tends to actually create inefficiency in the DSEM model, because missing data has to be inserted into the time series to create these equally spaced observations. So when you have a lot of missing data, it's just more difficult to estimate the model. But generally, it's not a problem, but it's just less efficient, and it's caused by choosing a sampling design that is less optimal for this particular model. And one thing to consider here is that there's some published articles about these hypothetical expectation biases that are created when you don't randomize the times of observation. And that, I think, is something that has to be studied further, because it's kind of like pushing us over the edge in a way that is forcing people to use less optimal sampling designs. But there's also a couple of other ways to deal with this. Is to actually have a more stable measurement instruments that would be less, prone to these expectation biases and less reliant on the particular time of observation. And another way to deal is also to actually include latent variable VAR models instead of observed variable VAR models, because if you include the factor analysis model, that's a very good way to create to take out measurement error. The model has also this brilliant causality implication that I'm personally fascinated with. And I'll just kind of, if you can kind of think of these two variables that I'm going to, suppose that the two variables that we're modeling here are stress and also poor sleep. So, and go back to this diagram here again. So stress and poor sleep, and basically you can discover which comes first or how do they feed on each other. So basically this will be these relationships here, which, because you have this timestamp, if this actually becomes large and it's causing this to be large, then you know that this variable is actually causing that other variable in a way. And, we're not saying that there's no other causations and things like that, but in terms of actually discovering how the two variables feed on each other across time would be something really viable. And it has the flavor of this causality that is really difficult to actually obtain in other ways. But definitely you can address which one comes first between, spikes in, say, stress or poor sleep. And then the other thing I wanted to bring up here is that the subject-specific random autocorrelation, so these are the subject-specific random autocorrelations, they can actually turn out to be quite important concept. When we started about this, and I was learning about, Alan Hammaker was kind of a tutor about, applications and what is important, and they always insisted that this is super important for them. One of the examples I remember from discussing it with this with her is that high rumination autocorrelation is actually associated with depression. And then, so the fact that these are random effects actually has quite important practical aspects. As a mathematician, then my problem with this whole thing is that, when you have a multi-level model, these coefficients are not always necessarily random. And so, it can happen that some of the variances of these random effects are zero, and they basically, when they're zero, then it's a constant across individual, and then you cannot use that as a predictor of anything, or you cannot correlate it with anything because it doesn't have any variance, right? So it kind of, one has to be cautious about estimating these models, even in the most basic situations. Next, I'm going to address how the latent centering actually works for DSEM. And basically, here's the Mplus Latent centering, which is essentially that's the autoregressive equation, just with one variable here, and it's the autoregressive equation on the within level. If you move the mu I here on this side of the equation, you get the within portion of the variable be regressed on the within portion from the previous period. And so this is basically the Mplus centering, which basically uses this random intercept not just as the random intercept here, but also it's using it as part of the predictor here. And the observed centering, which has been used in the past for panel time series data, is basically to replace this portion of the random intercept with the sample mean for the dependent variable. And when you do that, you can actually, you're in a very good situation because you can use now, this becomes a standard hierarchical linear model, so you can actually estimate it. But as you can expect, you're going to introduce another bias here, again, for the same reason that Lütke bias occur, because you make this predictor to be a predictor with certainty, and you don't account for the fact that there's uncertainty in that predictor that would come from the fact that the random intercept is unknown. And just a quick note here, because I'll forget to say, is that this observed centering situation kind of collapses anyway when you actually have missing data, because when you have missing data, you don't want to go here, with this sample mean, because this any kind of a missing at random is going to be a disaster for the observed centering. And again, just to summarize the two separate biases that we're talking about with the latent centering. So Lütke bias is for two-level and also for descent models, which are of course two-level models, and involves two separate variables, and the bias appears on the between level. But again, I showed you that the bias can actually spread out quite easily when the model becomes slightly more complicated. But the bias generally is on the between level, and then Nikel's bias is for descent models. It involves just one variable, and the bias actually occurs in the autocorrelation parameter, so the mean of these RIs. And that's the formula for Nikel's bias. And the biases are quite similar in the way that they both stem from not accounting for the uncertainty in the predictor, and both disappear when the time series increases, but both can appear in parallel in the same example, in the same model, but both can be solved with latent centering. So there are a lot of similarities between these two. Here's a little simulation that kind of illustrates how the Nikel's bias, as you can see, when the time series is 10, 20, 30, 50, you get fairly substantial bias in the autocorrelation coefficient, and the latent centering it outperforms here. And also you can see that Nikel's formula for approximating that bias is very close to what actually occurs. But latent centering pretty much eliminates the Nikel's bias completely. Next, I'm going to talk about the residual dynamic structure equation models, and the difference, the descent model and the R-descent models are fairly similar. The only difference is on how we actually do the within level model. And with the R-descent model, we separate the contemporaneous relationships between the variables from the time series relationship of the variables. So we separate the structural part of the model and the time series part of the model. And this is done as follows here. So here basically the structural models for the contemporaneous variables, and then we have these residuals which we call the hats. These are basically the residuals, and those residuals are then themselves modeled as in DSEM, where basically they have a time series model where those residuals can be regressed on the same variables from the previous periods. And those formulas kind of look like a mess, but I'm going to give you a very quick and simple example so that you know again what the difference between the two models is. So we have a simple regression, y variable and an x variable. The y variable is separated as between and within, and in the DSEM model, the within portion of y is predicted by the covariate and the dependent variable y from the previous period. And this is just one equation that includes both the covariate and the autoregressive relationship. So it's in the same equation. And if you actually consider what happens to the expected value of y given the covariates, you can see that it's this formula, and the reason, so you have that portion, but then the covariate from the previous period affects this variable, and so it's going to affect y, the current value of y, and so basically all the covariates end up being a part of this conditional expectation, which is a little difficult to interpret. And with the RDSM model, it's a lot simpler because you have y within be regressed on the predictor here, and then you have the residual, and the residual has the autocorrelation basically. And in that case, the conditional expectation of y given x is a very simple thing. It's beta times x, which is just like in standard regression. And so this is the basic advantage of the RDSM model, that it's very easy to interpret. The next thing that we're going to talk about here is that I'm going to compare the RDSM model and the RDSM model and the restricted maximum likelihood estimation. So they both estimate actually the same model. So if you consider just a simple covariate and just one dependent variable, we have this random intercept model with non-random slope and an autoregressive coefficient. And so basically that's the same model that the Remo estimator is used to estimate repeated measures longitudinal models. And however, the Remo estimator cannot accommodate random autocorrelations. And as we mentioned, before in psychology or in social sciences, these autocorrelations are generally individually specific. They would have some variation across individuals. And so we wanted to see with this simulation study, what's the effect of ignoring the random autocorrelation. And you can see in this situation that when you ignore the random autocorrelation, you get biased results for, this is the bias, this is for the mean autocorrelation parameter. So you get poor coverage also. This is the coverage of the estimates, and also this is the mean square there is also increased. So we conclude that Remo is not really suitable for data where the autocorrelation is subject specific. However, even in this case, the second important parameter here, beta 1, is estimated, gets the same estimates as RDSM. So there's no difference between RDSM and Remo when it comes to this parameter. Next, we actually going to do slightly more in this simulation. We're going to include a random, not just random autocorrelation, but also a random variance for this. So the residual variance in the autoregressive equation will have will be subject specific. And in that case, the situation is somewhat worse. First of all, the biases become much bigger for the autocorrelation parameter. And that actually, so this row 1 and row 3, you can see the bias gets quite a little bit bigger. And that actually is well known. So, well, it has been documented, I believe, probably at least 6 or 7 years ago. There was an article by Jorgen that actually pointed that out. And if they, the bias actually occurs when there is a covariant correlation between the subject-specific autocorrelation and the subject-specific residual variance. When there is such a correlation, then you get this kind of a bias in the autocorrelation parameter. The issue here is, though, that what we found out is that also with this simulation is that in this situation where both the autocorrelation parameter and the subject-specific variance, we have subject-specific variance, then not just the autocorrelation parameter is affected, but also the regression coefficients. And they're actually affected only in the mean squared error. So that the third column here is the mean squared error, and you can see it doubles. The parameter is still unbiased and the coverage is good, but the mean squared error gets much worse with Remo. Then we conducted also some simulation study to see how it works with categorical data. Because these packages that actually software packages that implement Remo, so SAS and SPSS actually have the Remo procedure. They do claim to be able to also estimate this with categorical data, and so we consider we wanted to study also how well Remo works with categorical data, and it turns out with categorical data the situation is much worse for Remo. So. And again, here we have this binary a binary variable, and you have the probit model, random intercept, a non-random slope, and a covariate, and you have the residual, the autocorrelation is introduced here to the underlying latent variable. So the residual basically in that regression, and it's autocorrelated across time. And you can see the Mplus results here for the parameters. They're pretty much unbiased everywhere. And you can see that the biases that you obtain with SAS and SPSS can become quite bad. And perhaps the two parameters are on side here, which is the variance of the random intercept are the two most sensitive. But you know, REMO is not quite a functioning estimator for categorical data. In this simulation, I did not include a random autocorrelation, so that the correlation was the same across individuals, and the results were still pretty bad. So now I kind of went in and showed you these simple models here, but those weren't actually the full models. So you can see like a model like that. That wasn't quite the full model, so I will ratchet up slightly. We're still going to have just two variables, y and x. But we're going to actually now start talking about the real situation where we are going to basically add to the previous models that we discussed. We're going to add contextual effect, latent centering, and we're also going to add the autocorrelation for the covariate. I mean, x, you know, is another variable that basically is you know, coming from a time series panel, and so assuming that it doesn't have autocorrelation is naive. And so we're going to now include the full model that that incorporates the full structure of the data. And so we start again by separating the dependent variable into a within and between, and we do the same thing for the covariate. And we have a regression from on the within level between the two components, and the regression on the between level. And then we include the autoregressive structure in the residuals for the dependent variable y. So that's the Ry coefficient, the autoregression for y. And then we also include Rx as the within portion of the x, which is basically because x doesn't have predictors, it's just the within portion of the covariate. And so basically, even though it might look slightly more complicated, the reality is that this is the simplest but comprehensive time series panel regression model. And in Mplus, that will be estimated with our descent. Again, the VAR model was a sort of a version of a bivariate model where you don't have a particular variable that's considered a predictor of the other variable. So it's kind of two variables that have equal consideration, where here we're talking about a predictor and a dependent variable. So it's a slightly different situation, but that would be the most simple situation for two variables for time series panel data.
Tihomir?
Yeah.
We've got a couple of questions here, and so I was wondering if this might be a good time to just
yes.
Are you happy to take questions? Yeah. Okay, great. So the first one is from Craig Sewell, and he's asking, does the DSEM assume a time invariant person-specific mean? And if so, is there a way to incorporate a moving average component, such as in ARIMA models? And obviously, you're going to get to that, but I just wanted to well,
you know, I mean, we do have. I won't be talking about the ARIMA models, but we do have in some of the papers we do have you know, particular way to deal with you know, with ARIMA models, and you know. Yeah, it's slightly more technical to actually go into that, but there's, you know, one of the ways to actually handle it is to, you know, include a latent variable, and the ARMA model turns out to be equivalent to a latent variable behind the observed variable, and then that variable has an autoregressive structure. So there's all these, you know, viable options in the framework. So. And you can include, you know, time-specific predictors also. Not sure if that is sufficient, but we do talk about these models actually in our papers.
Right, and there are as well examples in the Mplus manual for anyone who wants to go and see those there. And the next question is from Pete Koval, and he's asking, under what conditions would RD-SEM be more appropriate than DSEM? For example, is RD-SEM advantageous when the focus is on the contemporaneous effect of a within-level predictor and not on the autoregressive effect? Whereas DSEM, would it be more relevant when the focus is on autoregressive and cross-lagged effects?
Yes, the answer is a simple. Yeah, the answer is yes. And I'm actually, my next two slides are regarding exactly that. So, can I just continue from here on? Because yeah, that's basically. So here is, you can actually, we're actually doing exactly this now. I'm going to talk about comparing RDSEM and DSEM and figure out how they behave in different circumstances. And we are basically using, again, this model that I showed you before, but it's a fairly comprehensive model. But it's what we call, with this simulation, we demonstrate something called the exogeneity advantage. And what we call exogeneity advantage is kind of a concept that we haven't really experienced with our models, and we don't claim to understand a lot, but we do now know that this exists. So in most models, when you have a dependent variable covariate, you want to actually model just the conditional distribution. You don't generally prefer, we don't prefer to model both variables at the same time, because it's just less parsimonious and you will expose yourself to more misspecifications. And you generally prefer to just model y given x. It turns out that if you do that, you're better off doing it in the RDSEM framework. And so this is what that table is. And basically, we are basically, again, here the first column shows what the results are with DSEM, and the second, these rows here show what the results are with RDSEM. And you have different kind of situations here. So we introduce missing data, and this is basically missing it completely at random. Just 50% missing data completely at random, and under different scenarios here. And these are basically the biases that occur when you include both Rx and Ry in the model. Then both methods work fine. But then what happens when you drop either Rx or Ry, or you drop both of them? And what you can see is in the upper corner over here that the biases are larger, and the bold part, the bolded numbers are those where you also see problems with coverage. And so you can see that DSEM is actually more susceptible to this misspecification. So unless you want to do a full modeling for both X and Y, then you're better off doing it in the RDSEM framework. So that was one advantage that I want to point out. And we have another advantage that we are very well aware of, is the fact that the RDSEM is less sensitive to types of observations. So I mentioned random types of observations before, and the fact that Mplus would actually make a discrete grid and try to approximate these types of observations. And we have a command in Mplus called t-interval, and that is represented in this simulation by this delta. So delta equals 1 is basically a perfect grid. We've approximated the times of observations exactly. And as it grows larger, then at infinity, basically it ignores the distances in the times of observation. It assumes that all the observations are equally spaced. And you can see how the beta 1 and beta 2 parameters are affected in that very basic model. So RDSEM quite robust when the times of observations are specified, not the same thing for DSEM. So that's another kind of a little advantage that RDSEM has. But also Peter Kolos pointed the other one, which I don't have a slide for that particular thing, but that the contemporaneous relationships are, much easier to deal with RDSEM and much easier to interpret and understand. And here's one more simulation that kind of a sort of a messy paper again, but it's again the same model, the very simple regression model for the time series panel data. And we are basically just giving different values for Ry and Rx here, including contextual effect or not. And we are basically testing 4 different methods. And the first one is the RDSEM, basically latent centering with the autocorrelations. Then we drop the autocorrelations and see what happens to the estimates. And this is basically just for the parameter beta 2. And then we also, this estimator is basically using observed centering without the autocorrelation, which is essentially equivalent to a multi-level model, a simple multi-level model. And then we also have the RAMO estimator, which basically uses just observed centering and includes Ry in the correlation. And you can see that all these three have quite large biases, and that RDSM does the best. If you stare, the numbers quite a long time, then you can figure out the conclusions, but they're based on this page. So first, we see large contextual bias when you have autocorrelation in the covariate, and that bias is for MO, for observed centering, and the multi-level models. And the bias depends on the size of Rx, but it can be basically much worse than Lütke's bias, and in this simulation is 6 times larger. The bias tends to disappear as the number of time points increases, but much slower than Lütke's bias, and it can be found for even 100 time points, which is this row right here. You can still see the bias is still present, and coverage is hurt for these 3 estimators. And the bias, again, would occur due to not properly accounting for the measurement error in the covariate. And of course, it won't take long to realize that Rx is making the measurement error much worse. So in conclusion, also, one thing is to note here is that there's a common misconception in repeated measures modeling, and we tend to focus on Ry, while Rx is generally ignored. But in these simulations here, you can see that Rx is actually the one that's more important between the 2 autocorrelations, which one to account for. We also have an explicit formula that shows that can actually predict what the bias in the contextual effect is, and it looks like Lütke's bias, except that the T star is replaced, the size of the clusters is now replaced by the sort of effective size of the clusters, which would include the autocorrelation in the covariate here. And here's kind of this graph actually shows the relative contextual bias as a function of the interclass correlation. This is for when Rx is 0.5 with 30 points in the time series. And this is basically how the ICC of the covariate would affect the bias in the contextual effect. And you can see the ICC is, for example, 0.10. The relative bias is 50%, which basically can become quite large. So this actually concludes my discussion of the dynamics modeling, and then just brief mention here about our interaction framework, the latent variable interactions are quite easy to handle with the Bayesian estimator, because within the Gibbs sampler, within the MCMC, when we usually update one variable at a time, one of the latent variables at a time. And when you have a product of variable 1 and variable 2, to update variable 1, you essentially condition on variable 2. And so the conditional distribution for variable 1 actually it's explicit, and it doesn't have a product of 2 latent variables. So the Gibbs sampler is like a perfect tool to actually deal with interactions of latent variables. And it's quite easy to do to estimate SEM models with any number of interactions for single or multi-level models. And here's a little diagram with a simple model that has 3 latent variables that are measured by have their own measurement models, and then the 3rd latent variable is predicted by the first 2, and then it's also predicted by the product of the 2 latent variables. That will be kind of a very basic SEM model with interaction. And again, these are quite easy now to estimate with the Bayesian estimator. And to be honest, I can't quite remember if we actually meant this to happen, but it turns out that our biggest application for this interaction framework came to be that we were able to improve on the current state of moderation in 2-level models. It could have happened by chance. I have to go back and try and figure out if we actually meant that this will be the large benefit of this. But anyway, it just happened so that, so these are a couple of the articles that introduced multi-level moderation. And then here we have an article by Mike that introduced, and others that introduced the multi-level moderated mediation. And so those models have become quite popular. And in this article, the models were estimated with the maximum likelihood estimator. But it turns out that the direct Bayes is a much better way to do, and actually the maximum likelihood estimator is not very capable of actually dealing with the multi-level moderation models. In this article, the authors tried a two-stage estimation using Bayes methods, but again, it turns out that the direct Bayes method is much better. I'm actually going to show you the example here from Mike's article and some simulation studies. But so here we have 4 variables: dependent variable, moderator, mediator, covariate, and then a mediator. Moderator, sorry. So mediator, moderator. This is the moderator. And basically, we have the mediator here, M, is moderated by the variable Z. So the effect of X is moderated by the moderator Z. And the same thing happens for the Y variable here. So we include these interactions where the moderator affects the coefficient, the predictive coefficient for the covariate and the mediator here. And so we have these, here we have these interactions of latent variables because, again, those are latent variables. And so essentially, these are latent variables as well. And the latent variable interaction framework should be able to handle such interactions fairly well. On the between level, you can construct the same kind of a model with a moderator and the mediator, and the moderator is actually affecting the coefficients for the predictor for M and Y here. And so I'm going to show you the simulations. We compare the direct Bayes, which has almost no bias and works quite well. And then here's the Bayes with the two-stage estimation, which is the two-stage estimation basically comes up with imputed values for this. But the problem is there that, you know, the imputed values are constructed without the interaction variables. And so it doesn't work as well. And there's some biases and a decrease in coverage. And then the third estimator we compared is basically using the maximum likelihood with observed centering, but that also fails because of the stuff that I explained before about observed centering. But when you use observed centering for this kind of model, you can just, the model becomes quite simple because those are just the sample means, and you can essentially turn this model into just a standard two-level model. But unfortunately, it doesn't work well as well, has biases. And finally, this is going to be the last portion of my talk. I'll just quickly talk about Bayesian extension for the logic, the nominal, and the count variables. And oh yes, 1 second. I want to point out here that we're doing something that is going to be pretty important about these models. So, you know, at Mplus customer support, we actually get a lot of the models that were originally written in these papers, and people are trying to estimate it the way that the authors actually estimate it. And how often does this model come to Mplus? They're probably at least 3 or 4 times a week. And what we're actually doing, and we're planning to do quite soon, is actually construct a special website that we're actually going to give the Bayesian how to estimate these models with the Bayesian methods, and kind of provide more inputs and more direction to for these multi-level mediation models. And so this is something actually we're going to do quite soon. Anyway, so let me just quickly go over the last part of the talk, which is basically the Bayesian estimation for the logic, nominal, and count variables. So the first thing to consider here is that how does the Bayesian estimator estimate the probit regression? It takes the probit regression and it converts that regression into a linear regression by using that concept of underlying latent variable for the categorical variable. So the categorical variable, when you talk about probit regression, you can say that this is basically that there exists a normally distributed, conditionally normally distributed latent variable that is basically chopped up according to certain threshold values to obtain the categorical values. And so, and that makes the probit regression really easy to estimate with the Bayesian estimator. And for the longest time, we've actually wanted to do this with other variables. And we follow the literature, Bengt in particular follows the literature on this stuff. And, for the longest time, there was nothing coming out. Nobody's coming with any good ideas. However, very recently, now we have a solution for that. And it comes through this breakthrough due to the polar gamma distribution. And the polar gamma distribution is basically this infinite sum of gamma deviates. So a polar gamma distribution has two parameters, B and C. And if you can, gamma k here are gamma deviates, and you have this infinite sum. And the gamma deviates use the parameter beta, and the parameter C comes here in the denominator, so it's a weighted sum. And we have now also extensive algorithms for actually generating these efficiently generating gamma deviates without actually having to use this infinite sum, of course. And how does that actually help? Well, here is how you can convert a logistic regression into a linear regression. So here's a binary variable, and that's basically the logistic regression. And we generate, the first step is to generate a polar gamma deviate with these parameters, and then we construct a latent variable y star using this formula. So it's just a binary value y minus 0.5 divided by square root of w. And it turns out that the logistic regression for y is converted to a linear regression for y star. So y star here is conditionally normally distributed, and epsilon here is the residually standard normal. And the only difference between this logistic regression and the linear regression is that we change the covariates, so we multiply the covariates by square root of w, but the parameters that to be estimated are the same. So this construction actually allows us to convert the logistic regression into a linear regression for y star, and from there one can basically incorporate this into a generalized framework, and that's what we want as a framework sort of for people. And here's how this also works. There's also trivial generalization that does these nominal variables, and this also works with negative binomial distribution for so count negative binomial Poisson regressions. So if you have a negative binomial regression, so which kind of like we call this NB beta x here, where alpha is the dispersion parameter. Again, we generate a PG deviate using these parameter values, and the latent construct is computed using this formula. And then the negative binomial regression is then converted into a linear regression for y star. So it's got again the same coefficient beta, and we basically have the covariates are again multiplied by x, and this is a standard normal distribution for the residual. So we got this methodology. I'll just show you a little bit, two brief examples. And this is basically, again, it's a time series panel data with count outcomes. And we have YIT is a count observation for individual y at time t. And we can actually construct sort of a descent model for these count variables, where this is a negative binomial. Again, how we write the negative binomial regression, but essentially the expected value of YIT is the exponent of this thing here. And this represents, again, the subject time invariant, subject specific random intercept, which is modeled as a normal latent variable. And then the residual here, it has its own autoregressive model. This model, just like the descent model, can separate the correlations that are due to observations nested within observations nested within person from those correlations that are due to observations taken in proximity of time. And you can see a little simulation here that the Bayesian estimator works quite well. These are the minimal biases and pretty much coverage close to the nominal levels. And the last example I want to show you is that we using the same methodology. Now we can actually finally estimate. We can include nominal variables quite efficiently in multi-level models. And here's an example with the nominal variable IAJ for individual I in cluster J. We have a covariate, just like before. We split the covariate as a within and between. And then both of these covariates now will be used, both of these are latent covariates, and they'll be used in the nominal regression with separate coefficients. And so the model actually features, first of all, contextual effect, where the coefficients are separate for the within and the between. It features also latent centering here for the covariate. And we also have the cluster-specific random intercept and random slopes. So a model like this, if you try to estimate with the maximum likelihood estimator, it will give you a 5-dimensional numerical integration. So it will be really hard to do, very computationally intensive. But with the Bayesian estimator, it's pretty straightforward. Here's a little simulation. Okay, so sorry, I meant to say that in my simulation, I use a nominal variable with 3 categories, basically. So the 5 random effects will be for the first and second category, intercept and slope, and then the XB also is an additional dimension of integration. But again, nominal variables can be handled quite easily in multi-level models now with the Bayesian estimator as well, which I think is an important breakthrough. Due to the polar gamma distribution. And to summarize my talk, Bayesian estimation enhances our ability to find correlations in the data that the maximum likelihood estimation cannot. The Bayesian estimation allows us to, for incremental modeling advances, while the maximum likelihood estimation does not. Which basically a slight model complication can actually make the maximum likelihood uncomputable, while the Bayesian estimator usually can be modified to actually include minor modifications. And then the Bayesian estimator is also uniquely suitable for modeling with latent constructs, factors and random slopes and loadings. In the MCMC, Gibbs sampling latent variables, once they updated, they become they treated as observed, and that makes the Bayesian estimation a winner in these situations. And because of these points, I think there'll be further developments to come in this area, and some of it will come from the Mplus team, but I'm sure other people will contribute just as much in that area. So, and with that, I conclude my talk. And if you have questions for me, let me know. Thank you for your attention.
Thank you so much, Tihomir. So let's open it up for questions or comments if anybody has any. I'm always happy to get the Q&A started, but certainly if anybody else would like to jump in, what we can do here is, instead of typing your questions into the kind of the Q&A text editor there, we can I can, if you raise your hand, I can I think allow you to appear. And so if anybody has any questions.
Mike, let me just add something.
Yeah.
We have a nice short course topic video number 12, I think it is, in 12, 13 maybe, where we go through DSEM and RDSEM in detail, and also show examples where there are trends in the data across time. So that would be a good follow-up for those who for whom this is a new topic.
Right. That's a good point. I mean, some people will be coming perhaps from econometrics, just given the diversity of the audience here. And so for them, they're often quite concerned by trends. And so they're estimating those ARIMA models, because when they see a trend, they're usually first differencing or for a stochastic trend, or otherwise trying to eliminate the trends or account for them. Okay, well, I'm happy to ask a question, and that is, so the first part of the talk is on DSEM, and then the second part of the talk is kind of on Bayes estimation, and that, well, specifically with for latent interactions. And what are the possibilities going forward for allowing for latent interactions in DSEM, specifically in the within part of the model, where we might want to estimate time varying changes in those AR parameters, or those lagged effects?
I mean, eventually it probably will get there. You know, I think there are some. I mean, I don't think that there's actually math, anything to do with math. Basically, it's just a matter of actually the software development. I think it's just, you know, I don't think that there's any complications, basically, to actually include interactions. It's just a matter of implementation, I think.
Right. I noticed that in version 8.6, you allow for Bayes estimation with multiply imputed data. So in theory, people could do kind of a two-stage analysis there with DSEM, generating plausible values and then using those as input. I don't know, what do you think?
That's right. So this is one alternative, and then the other alternative is still to use observed centering. So if you can't actually, if it's too complicated to actually construct a Bayesian estimation, or it's not available for some reason, you know, those are valid alternatives. And yeah, that would be one application. Just do, you know, impute the values and then analyze them with the Bayesian estimator again, you know, using those imputed values through the multiple imputation, or another alternative is just to use the observed centering and kind of construct these variables as observed.
Right, even if it's suboptimal.
Right, it's still, you know, you'll get to somewhere, you know, to see if there is something significant there. So.
Right. Okay, so we have a question that's just come in. Andrew, do you want to ask this yourself, or do you just want me to read it out? Let me. Tihomir, can you see the
Yeah, I can see it. As Mplus looked at the not sampler. I mean, we have considered it, but you know, it hasn't been something that. Well, so okay, so the in general, I'm not a very big fan of actually pursuing the priors, to be honest. And I, you know, you can be assured that Bank is bothering me all the time about this, but we generally, I'm not a very big fan that you can achieve something by specifying different kind of priors. Ultimately, we don't want the priors to be in there, because most of the time we can actually come up with good priors anyway. So. You know, that, and then the other sort of thing is the agency sampler. You know, it sounds like there's a lot of good work done there, and that those are quite efficient and very important improvements. But we you know, one thing to consider is a lot of these samplers, they are developed for particular models, and you know, we are still in a kind of a very general model, and we trying to actually accommodate some of these different samplers. It's a little bit difficult, because you know, they use gradients and things like that, and so it becomes a little more complex. And so, you know, a lot of these the sampling steps for these MCMC for these Bayesian estimators, the sampling steps themselves are much slower. They gain in terms of efficiency. And we are basically mostly using Metropolis Hastings when we cannot do an explicit updating, and that we generally are willing to spend a lot of time coming up with a really good Metropolis Hastings than to go to another sampler. So that's been our strategy, that we can make it really efficient if we actually really pay good attention of how to actually do a good Metropolis Hastings.
Okay, anybody else? Andrew, if you have any follow-ups, feel free to unmute yourself. And this sounds like a trade-off that you and your team must deal with all the time, is people have very specific modeling interests, and so specific algorithms, for example, for optimization might be good for some specific cases, but of course the point is generally kind of a general modeling framework. And so
yes, so it seems to us also, we generally have the other computational advantage, because it's we basically we're using Mplus is usually pretty fast compared to any other environment that you can actually run models in. And so it's difficult to evaluate different samplers that way. Again, it's because the iterative steps are slower, but they're better mixers. So we have different strategies. We try to one of if you're not familiar with what Mplus does, we actually try to make the largest block that we can make update at once, and that actually improves the efficiency. So we're not super. A lot of the times you're not super concerned with efficiency. Actually, most situations the efficiency is good. And it's a matter of fast iterative steps.
Right, and larger blocks also allows for more flexibility in the way that you implement constraints, for example, as well as, isn't that true? There are multiple advantages.
I'm not quite sure what you mean by constraints. We usually don't do a lot of
like parameter constraints, for example.
Parameter constraints. That's right. Yeah, that's great. Yeah.
Yeah, it's interesting. If you go to like the maybe I shouldn't name any competitors, but if you go to like the Stata web forums and stuff, you hear people saying, why can't you be as stable and as fast as Mplus?
Well, we do. I was just on your previous question. Do we actually want the biggest block? And sometimes you actually do a total opposite. We will do anything to gain efficiency. Right. So in certain situations, actually, it's better to do smaller blocks optimizations, small blocks updating. So it actually, it depends on the situation a little bit. So. But yes, if you have model constraints, then you cannot do smaller blocks, and then you have to do a bigger block. And yeah.
Okay, great. Does anybody have anything else? You've got Tihomir here, and it's kind of a unique opportunity to ask a question, so don't be shy.
There's one question here that I can see on my screen. The methods covered today suitable for time series with very rare events. Examples that happen on 20 different days over a lifetime or 30 years. I'm not really sure, but first of all, if it's a binary, we're talking about binary data again. I think we have spent a lot of time doing some of this hidden Markov processing. We actually do have if it's continuous data, we basically what we want to take advantage of with continuous data is when you have rare events is these subject-specific residual variances, because those will accommodate kind of like a constant behavior sort of thing, I think. But zero inflated time series. I have to tell you that these articles that I mentioned towards the end here, they do have some kind of, for example, zero inflated Poisson distributions have already been dealt with using this polar gamma methodology. There's a published article. It's not yet in Mplus, but it is possible to use the same methodologies to actually estimate it. So I'm not really sure what else I can say on that. My suggestion would be to consider as probably one of the main, most powerful probably method would be in Mplus would be to use the to model the variables categorical and then use this time series that is based on polychloric tetrachloric correlations, autocorrelations. But time series with rare events, I mean, it's you're starting, it's a hard problem, I guess.
Okay, great. What do you think? Should we call it a day? That's an hour and 40 minutes. What do you think, Tihomir?
Yeah, sounds good. And you guys, if you come up with sleep on it, and if you have more questions, we'll be back tomorrow. So we can talk.
Right. That's right. Bengt, do you have anything to add before we?
No, I just want to say I hope to see you all tomorrow.
Yeah, that's right. That's right. Definitely. And an advertisement is in order. We'll start again tomorrow, same time, same place, and or same places. And and thanks so much everybody for coming, and thank you Tihomir and Bengt for doing this, and Kirsten, and also I forgot to mention at the beginning in the introduction the Melbourne Centre for Data Science, which is co-hosting the event. I'm sure Kirsten noticed us. Sorry about that oversight. I'll get it right tomorrow. And we very much appreciate their assistance and support. Thank you so much, and we'll see you tomorrow.
Okay, thank you. Bye-bye.